Good morning, friends. I am here again for my course, Aircraft Systems. This course belongs to the sixth semester of Aeronautical Engineering from Institute of Aeronautical Engineering, Hyderabad. Today's topic is modes of operation of fuel systems. As you know, my name is Dr. Yagya Dutta Dwivedhi, professor from Institute of Aeronautical Engineering, Hyderabad, India. As of now, I have covered 30 lectures before that. If you see in that, I have started with Module 1. The Module 1 covers all the basic introduction of all type of systems used in aircraft like airframe or structural systems, vehicle system, avionic systems and the mission systems. We have discussed this all in a brief in Module 1. If you see about the Module 2 covers the basic electrical systems, power generation, AC-DC systems, power control, power distribution, emergency power supply, APU, batteries, bus bar, controlling devices, and so on. We have discussed in the Module 2. If you talk about the Module 3, we have discussed about aircraft hydraulic system and the pneumatic system. In hydraulic system, we have seen that what are the different types of components used for the hydraulic systems, hydraulic fluids, their advantages, disadvantages, property of the hydraulic fluids, different systems operated by hydraulic devices, and also we have covered the pneumatic systems. In case of hydraulic system is not working, that time pneumatic systems are used. In pneumatic system, we have seen that different types of components used in the aircraft like pumps, reservoir, then filters, accumulators, and so on. In the present module 4, we are discussing about the engine and the fuel control system, and we have already covered the engine control system. Now I am in fuel systems of the aircraft, and today I am going to take about modes of operation of fuel system. So this I have given a simple brief of my previous chapters which I have covered. In the present lecture, I am going to talk about fuel system for aircraft and introduction, single engine aircraft which are operating by gasoline fuel system, multi-engine aircraft, gasoline fuel system, turbine fuel system functions, refueling of the aircraft, defueling of the aircraft, and jettisoning of the aircraft. These I am going to discuss today and hope this will be very useful for all of the viewers. I also request that if possible, please like and subscribe this YouTube channel. I will get a lot of encouragement if you do so. Now I am starting with fuel system for aircraft and introduction. An aircraft fuel system allows the crew to pump, manage, and deliver aviation fuel to the propulsion system and auxiliary power unit. It is also called APU of an aircraft. Fuel systems differ greatly due to different performance of the aircraft in which they are installed. A single-engine piston aircraft has a simple fuel system. A tanker such as the KC-135, in addition to managing its own fuel, can also provide fuel to the other aircraft. So what is the meaning of this? That any aircraft fuel system, it has to pump the fuel of a given amount of pressure. Also, it is to be managed how and where, at what time the fuel has to go, and also to deliver a required amount of fuel to the aviation fuel system. Propulsion engine, like it may be the piston engine or the turbine engine or any type of engine, and also it has to supply the fuel to the auxiliary power unit, APU. These auxiliary power units are the small engines operated by the fuel system, and these engines are used to give the power supply in case of on the ground if the ground power supply is not available, and also during emergency of power supply during flight also this gives the emergency power supply. Not only this, few aircrafts are called the fuel tankers like KC-135. These tankers are also used to give air-to-air supply. When the aircraft is flying, these tankers will supply the fuel to the other aircraft in air itself. Fuel is piped through fuel lines to a fuel control valve, usually known as the fuel selector valve. This valve serves several functions. The first function is to act as a fuel shutoff valve. So this fuel selector valve is like opening of a water tap. Open or close, open or close. Same way, these fuel selector valves or the shutoff valve are used as a selection, means right tank selection or the left selection or the both tank selection at a time as per the requirement, and also in case of emergency the fuel can be cut off fully and the fuel will not go to the any system. So it is equipped in this way. This is required to provide the crew with a means to prevent fuel reaching the engine in case of an engine fire. Suppose the engine has been affected by the fire and engine has took the fire, and if the fuel is also going, the fire will be increased very tremendously. Too much fire will be there. To prevent that fire, we have to cut off the fuel supply to the engine so that backfire will not reach to the fuel tank. If it is reaching to the fuel tank, it will destroy whole aircraft. To prevent that, we have to shut off the fuel supply, and this is done by the selector valve. The second function is to allow the pilot to choose which tank feed the engine. So first is to give the feed to shut off, and second feed fuel from respective tank, whether left or the right. So this is also done by the selector valve. So the second function is to allow the pilot to choose which tank feeds. Which tank means left tank or the right tank, the engine. Many aircraft have the left tank and the right tank selections available to the pilot. So pilot will be able to select which, and this is done by the selector valve. So that is the purpose of the selector valve. Single engine aircraft, gasoline fuel system. I am going to discuss about this, and you will see that gasoline or petrol or the CNG or LPG is used for this type of engines. The fuel level indication system in the simplest form in aircraft is a transparent window on the tank side, and in its usual application a float driven potentiometer installed in the tank. After the TWA Flight 800 disaster, one accident happened. A revision was made to aircraft fuel systems to address the potential explosion hazard of electrical components located in the fuel tank. Single engine piston aircraft fuel level system moves to utilize float level gauge from the CNG and the LPG industry, which has the float drive a magnetic coupling and a relocated the potentiometer outside the fuel tank. So what happened? Previously, a fuel tank was used. In that, inside only one electrical resistance, and this resistance there is a float. Float will go up or down as per the float, like our water tank in our house. It was like that. So in that, it will go up and down the float, and accordingly the resistance of this thing will change and it will deflect in the pilot's instrument panel. But there was one accident, and this accident has took place in TWA Flight 800 disaster. In that, the fire has taken place inside the tank and the whole aircraft was destroyed. From that onwards, another system was used. In that, there is a magnetic coupling. This you can see here, this is the diagram here. In this, the float is inside the tank, this one is inside the tank, and this system is outside. And as and when the fuel will go up or down as per the burning of the fuel, this lever will go up and down, and outside this magnetic resistance will change and it will deflect in the meter. A fuel is burned, more air enters the tank and the capacitance increases. This is ready for a computer and the fuel amount is calculated and displayed on the pilot. Recent advances in magneto-resistive technology have evolved fuel level sensors for general aviation application. This is a new technology which is nowadays used for the measuring of the fuel level. In this we can see that as and when the fuel is getting down, the air level will increase and this air will change the capacitance of the system. And this capacitance is measured on the dial or in the instrument panel. And nowadays we have the magneto-resistive technology, and which is very nice. It is shown here. In this, the float is inside and the resistance of the magnetic will change and it will give the reading. And this is fitted outside of the tank, not inside the tank. Only this probe is here and this will go up and down as per the level of the fuel. So in this way, this system is working. Now I will talk about the multi-engine aircraft fuel system. We know that few aircrafts are having a single engine, few are having 2 engines, few are having 4 engines, few are having 3 engines, 6 engine, 8 engine also as per the size of the aircraft. So multi-engine aircraft fuel systems are much complicated. So I am going to discuss about the multi-engine aircraft fuel system. In this, adding tanks and engine increases the complexity of the fuel system and its management. Additional features found in multi-engine aircrafts are. So we know that if you have the more engines, more tanks are required and more tanks should be interconnected so that fuel supply should be a proper way and there should not be any CG variation or one side tilting of the aircraft should not happen. So this makes the system very complex. So what are the features of the multi-engine aircraft's fuel systems? Each wing tank often has its own electric booster pump. So for every tank, we will have the own booster pump. And each engine has its own mechanical pump. So engine-driven pump, for every engine, there is a separate engine-driven pump or the mechanical pump. For each tank, we will have the separate booster pump, replicating the fuel system described above for the single engine. So means just like for a single engine, if we have the 2 engines, so we will have totally 2 systems will be there. Every pump, everything for each system will be different, separate. In case of single engine operation, there is often a method incorporated to the cross feed the engine, left tank feeding right and vice versa. So if in case of one engine fail and the fuel will go from the left to right and the right to left. In this way, the system can be worked. To balance asymmetric weight, flow valves and pumps often are used to feed both engines from one tank or simply to transfer fuel between the tanks. So to balance the weight, sometimes we need the left side weight more or the right side of the weight more, or both are not balanced. So aircraft will be tilting in one side. That time also there should be a pumps, there should be valve. It should immediately shift the fuel from one tank to another or from another to the next one. Like this, we should try to make the fuel system such a way that the center of gravity and the mass of the aircraft is balanced. Now I will talk about the turbine fuel system. And piston and turbine, there is a minor difference in the system. So to avoid water condensation or the fuel itself solidifying at low temperature, minus 55 degrees centigrade. If you are flying the aircraft at a very low temperature, like Siberia, Antarctica and some other places, temperature is very, very low. So there is chances of the water which is mixed in the fuel, sometimes due to atmospheric condition, that water is going to be freeze, and this will cause a lot of problem for the system. Fuel tanks have thermometers and heating system. So fuel tank itself has the thermometer and there is electrical heating system, and this will try to heat. Many are pressurized with engine bleed air to keep moist air out and ensure possible pressure feed to the pump. Some of the tanks of the systems are pressurized from the bleed air and it is hot air, and so that the atmospheric air will not enter, and which will make sure that the positive pressure feed to the pump. So the atmospheric pressure is lesser than the inside, so your air will not enter. In larger aircraft, fuel tanks also are in the fuselage, and their load affects the center of gravity of the aircraft. This imposes limitation on the amount of fuel carried and the order in which fuel must be used. Turbine engine burn fuel faster than reciprocating engine do, because fuel feed to the injected into the combustor. The injection system of a turbine aircraft must provide fuel at a higher pressure and flow operated to that for a piston engine aircraft. So we know that in the turbine, how the turbine is working and what are the components. Just I will draw a small diagram. Here is the compressor. There are number of stages of the compressor. I am showing only 3 here. And there is a combustion chamber. I am writing CC. And then we have the turbines. Just I am showing the 2 stages. So air is entering from here and fuel will enter here from injector. This is the fuel line. Fuel will be going here. It is the injector here. It is called injector. And here we need a very high pressure for this system. So in gas turbine engine, this is the turbine. I am writing T here. And these are the compressor. I am writing C, CC and fuel injector. So turbine aircrafts must provide fuel at a higher pressure. So we need a very high pump, that is called the engine driven pump, EDP. EDP, engine driven pump. It is very high pressure. Some 100 bar pressures are there. This 100 bar pressure will try to pressurize this system and the system will give a very good injection system. Now fuel system functions. What are the functions of the fuel system? So the main functions are the fuel transfer, engine feed, fuel measurement, fuel management, fuel jettisoning. So these are the few functions which are mentioned here. So transfer of the fuel from one tank to another, from high side to low side. In case of one system is failed, another system should start. Engine feeding, proper amount of fuel should be supplied to the each engine with a given amount of pressure. Fuel measurement, the quality of the fuel has to be sent, and how much quantity is available on the fuel tank, it should be constantly displayed on the aircraft cockpit and pilot should be able to see. And also fuel management, if the center of gravity is changing one side to another side, the fuel system we should be able to transfer from one side to another side and the vice versa, so that the center of gravity of the aircraft can be maintained. And fuel jettisoning, in case of emergency or engine is failed and pilot want that the weight is high and the pilot want that this should be jettisoned, there should be some mechanism in which the fuel should be removed in a very less time. So that fuel jettisoning also should be there. Here I have shown one diagram or one table in which this you can see that operator and the design requirement. It will go to aircraft level requirement, how much level of the aircraft. This can be seen by the pilot on the cockpit. Airworthiness regulations. The DGCA or FAA will formulate some policies. The fuel system should follow the airworthiness regulations. Also, the designer should understand that what is the operator requirement and what type of design we have to make it. Then it will go to the aircraft level requirement. From here, tank locations, where the tank to be located, the high wing or lower wing or the middle wing or in the fuselage or on the external fuel tanks and so on. All requirements we have to see here. It is called the physical constant. So there we can see the 4 constant. One is the airworthiness, physical constant, system functionality and equipment. So here we can see that tank locations and the fuel storage requirement. From here we can see the refuel and the defuel. Fueling means putting fuel inside and defuel means putting from inside to outside. It is called defueling. Engine and APU feed. Fuel should be able to give with a sufficient amount of quantity and the pressure to the engine and also auxiliary power unit. Fuel transfer and the jettisoning should be very easy from one tank to another tank, from another to another tank, and also from tank to the outside in case of emergency. We should be able to jettison the fuel. Currently, measurements and the indication. Quantity measurement and the indication, how much quantity is available on the fuel tanks, or how much amount of fuel is entering and how much amount of fuel is going. This all has to be indicated properly. Fuel management and the control. The fuel, in case of emergency, you should be able to shut off. In case of some other issues from one part to another part, we should be able to feed the system as per the requirement. Now from here, if you see the fluid mechanical functions and sensors, electronics and the softwares. So we can divide into this thing into 2 groups. One is the fluid mechanics problem and another is the electrical and electronics by using the computer, software and sensors. Here we use the pumps, valves and actuators, and here we use the avionics, sensors and harnesses. So this is a fuel system functions and how it is working. It is reflected here. Hope it is very much simple and you all can understand very well. Now, refueling and the defueling of the system. As I told earlier also, for every flying we have to fill our fuel tank. These fuel tanks are filled by the ground truck. These trucks are Bowser, it is called the Bowser. Bowsers are fitted with the fuel, maybe the jet fuel or the gasoline or anything. And so this from the Bowser we are putting on the inside the fuel tank. This is called the refueling. And when in case of we are doing some servicing or we need to reduce the weight of the aircraft during ground for the jacking up of the aircraft, we don't need the fuel to be there. Or during maintenance, if you are working for welding on the aircraft, we have to jettison the fuel or we have to remove the fuel. That is called the defueling. The defueling is removing fuel from the aircraft tank to outside. That is called the defueling. So these 2 operations are very important and we should make sure that proper precautions of these things are to be taken. So this refueling and defueling, here we can see that airport based ground refueling system, it is called hydrant. Underground pipelines are there and it is fixed with a meter. So we can take the hose and we can put inside their filling point, and in this way we can fill the aircraft by the help of the hydrant. Hydrant means it is a pressurized pump. Refueling prior to almost every flight. Every time we have to see that how much quantity of the fuel is available inside the tank. This can be seen from the cockpit instrumentation. And before every flight, we should see that the fuel is full. If not full, we should use the fuel Bowsers to fill the tanks. Time to refuel critical. So we should also refuel as per the time and we should see that how much fuel is there. Backup gravity refueling. So sometimes if it is not there, we are putting a big, very long tank. From there it can come the fuel without any pump. Another is the pressure refueling. In this we use the pumps, and quick aircraft turnaround time. So what is the benefit of the pressure refueling? Because it is by the very high powered pump, and it is giving in a very less time, within few minutes your whole tanks will be filled. So it is very quick. Aircraft turnaround time means aircraft has come within few minutes, your tank will be filled. Again, it is ready to take off for the next shuttle. Accurate load that matches upcoming flight, extra weight of unneeded fuel. In this, how much fuel we need from one place to another fuel. Keeping emergency fuel in the mind, we can fill that much amount of the fuel. Protection against overboard spillage, and also it makes that it is not leaking on wings or other places fuel, otherwise it will make the risk for the fire that we have to try to avoid. This can be used by using the pressure refueling system. Protection against overpressurization. We should not make the system overpressurized, otherwise there is a chances that the tanks or their pipelines or their some other equipments may be bursting. Compatible throughout the world. Your system should be in such a way that it should be compatible to all the people. Compliances with CG limits. We should make sure that the CG, the center of gravity, is given a proper limits. In that only aircraft should be filled. Residual fuel from previous flight. We should make sure that how much fuel is left. Accordingly, we have to refuel the system again. So this is refueling here. I am showing here one diagram in this. It is called the DiNozzle. Here, this is from the fuel bowser. This is the fixed in a truck here. Okay, this is in a truck, and this truck is filled of fuel, and this nozzle is inserted here inside the aircraft. It is a refueling point. This is the refueling point, fuel bowser, and here we have some safety devices and all. So it is called the DI nozzle, and in this nozzle, this is the nozzle, and this is inserted inside the aircraft. Embraer 190 refuel station. Okay, so this Embraer aircraft 190, the refueling is done in this way. So it is just shown for a pictorial representation of the ground refueling station on the aircraft, and from the ground this hose is taken and this hose is connected to the aircraft. Fuel system architecture. Fuel entry points, high level sensors, balance tubes. This we can see here that wings, we have the high level sensor here. Sensors are here. It will indicate that how much level of the fuel. Balance tube is here. This will balance the wing. Then we have the rising fuel level. Then we have refuel shut-off valve here. This we can make on or off. Initially, the inboard fuel tank and the collectors cell fill first. First inboard. This is the first, then second, then third. First inboard will, then the next. Same way here. Example of the use of the balance tubes. So how this balance tubes will work? Here is the collector cell. Then here rising fuel level. And here is the balance tube. This balance tube will make that as and when it is filled here, it will come here, it will fill, and then it will go here, and then it will fill here. It will not come here. It is from here it will go to the last, and from here it will go here. In this way, the balance tube makes that the aircraft wing are balanced with equal amount of fuel in as per the design conditions. Refuel and transfer systems. Aircraft refueling means putting the fuel inside the wing. It is called the refueling. And how it is transferring from one to another, it is called the transfer. So refuel completely passive in flight. Refuel system combined with in-flight fuel transfer system. So this you can see that we have here the transfer pumps. This is the inboard. This is the outboard. And this is the mid tank. So first this will fill, then this will go to here, and from here it will go to here. So like this, transfer pumps are there. Common refuel transfer gallery, ground refuel adapter. So here I have shown in this previous diagram here. This you can see, this hose is entering here. This hose. It is called fueling hose. Fuel hose is attached here, and in this way these systems are working. Failure modes, there are some failure modes are also there. Shut-off valve is also there. A special venting configuration to prevent overpressurization pre-checks. So we should also have the venting system so that the overpressurization should not be there. If there are some problems, we can shut off these things. We should also do the pre-check before flight. We should understand that there should not be any problem. Shut off flow prior to reaching the selected fuel quantity. It should be in such a way that you select some quantity, automatic your fuel input should be stopped, like our petrol pump. You just give the 500 rupees, exactly 500 your hose will stop. The same system was used from very long time in our aircraft, and it will give a required amount of quantity inside the tank. Refueling system design. Refuel and defuel requirement, we should know how much refueling is required, how much defueling is required, and in what condition we need the refueling and the defueling of the aircraft, derived from top level aircraft configuration and operational requirement. And this refueling is defueling is done as per the operational and configuration requirement of the aircraft. Use of electrical or the fluid mechanical equipments, of what type of pumps, valves, these things should be called the fluid mechanical equipments, and the electrical, the avionics, sensors and other things are also used for this purpose. Now I will talk about the defueling. Till now I have talked about the refueling is filling the fuel inside the aircraft. Now the fuel is inside. Suppose this is the aircraft. We have here all these tanks are filled, and if we feel that some emergency is there, out of two engine, this is the engine 1, engine 2, one engine has failed and there is some turbulence in the atmosphere, that time what we will do? We have to reduce the weight of the fuel. So there is a defueling, or whenever we want to do some maintenance work on the ground, on jacking up, especially for the rigging of the control or pressurizing the landing gears or charging the landing gears or some maintenance in the landing gear, that time we have to lift by the help of jacks. So if your aircraft is filled with the fuel, it is very dangerous. So we should defuel the aircraft in these type of conditions. Okay, so first thing is the maintenance, and I have just told you what are the maintenance in which we have to defuel the aircraft. So if you want to calibrate your fuel sensors, fuel quantity sensors, that time also we have to defuel and the fuel. If you want to change the landing gears, any components, or we want to charge, or we want to pressurize, that time also. If you want to do the control rigging of surface control, elevator, aileron, rudder, or the fuel system control, if you want to do some rigging, that time we have to defuel the aircraft. So these are part of the maintenance. Overfueling in error. Sometimes due to the unknown or some wrong orders are passed, aircraft is more fueled. we have to take out some fuel. That is called the over fueling. Due to some mistakes, that time also we have to take out the fuel. Following an accident, if any accidents happen, that time also we have to remove refuel defuel point to allow access, wheel up and the landing. Pressure or the suction defuel. So there are two types of defueling. One is a pressure defueling from the aircraft itself. There is a pump and it will defuel, or sometimes from outside it will be sucked by some additional device or some defueler on the ground. Defuel flow shut off. Defuel flow shut off also we can do. Feed pumping system. We need a system which can feed the pump. Here we have the booster pumps. These booster pumps are immediately after the tank. This is the tank. And after the tank, this is the booster pumps are fitted. These booster pumps are fitted to give a positive feed to the engine. There should not be any time vacuum. Otherwise, the air will be trapped and the system will malfunction. So, booster pumps should be there. Then motor-driven pumps or engine-driven pumps are also required. Then ejector pumps are also required. It is a jet pumps. So, these are the different types of pumps. Ejector pumps are used just before the combustion chamber and it gives a very high pressure to the fuel and it will be atomized. That time we use the ejector pump, and from pump to the ejector pump we need some more pump, that is called the motor driven pump or the engine driven pump, and the booster pump is required to give a high pressure, a slightly higher than the atmospheric, to give a proper smooth supply of the fuel in all the pipelines. Next I will talk about the engine and the APU. Engine, you know, and APU is auxiliary power unit feed. How we give the so here this you can see here that this is here engines are engine feed tank locations. Here is engine location. So this has to go from here to here, fuel from here to here. So how it will go? This is, I want to, rear engine aircraft with negative pitch angle. If the nose is down, fuel will try to go in this direction. But we want to supply in this direction. Engine is here. So from tank to fuel, how it will go? This is we are going to discuss. Auxiliary power unit is electrical power when aircraft on the ground. This purpose of the auxiliary power unit is to supply the electrical power when on the ground. In ground, we should not start the main engine. Additional electrical power in flight, engine driven generator inoperative. If the generator is inoperative, that time also APU will function and it will give power to the electrical devices. Air conditioning on the ground. Once we are on the ground, we will not start the aircraft main engine or we will not start the engine driven generator because these are operated by the engine. So that time we will start the APU and APU will make that air conditioning of the whole aircraft is done. Air turbine starters are also started by the auxiliary power unit. APU start, then fuel pump will also be used. These fuel pumps are used to give the higher pressure to the APU. Feed tank and the engine location. This I have shown here. The feed tanks are here in this wings and engine is located, and if it is nose down, more pressure is required to supply the fuel. Each engine has its dedicated feed tank. Aircraft with rear mounted engines, like here I have shown here, it is a rear mounted engine. So if the engine is rear mounted behind the wing, long feed lines are required. Large variation in fuel pressure during aircraft pitch. If it is nose down or so more pressure is required. Fuel pressure at the engine interface above the vapor pressure. So more high pressure so that the pressure is crossing the vapor pressure of the system. Here we can see that motor driven fuel pump schematic is shown here. So this I am going to discuss. So here high volume flow is required, low pressure and high reliability of the pumps are required. Mounted on the lower boundary of the feed tank, easy removal without drain on the tank. Spar mounted pumps, performance penalties are there. Ability to operate with air or vapor at inlet or no inlet fuel head, rotor failure condition, motor winding over temperatures. Fresh kerosene can obtain 40% of air by volume at sea level. So we are using the ATFK, aircraft turbine fuel kerosene 50, and this ATFK can take 14% of the air it can absorb in the sea level. So we should be very much careful. 14% is huge amount, and this much if air is there, maybe some 1 to 2% of the moisture will be there. So aircraft climb, air bubbles out. Once the aircraft is climbing and your ATFK is mixed with 14% of the air bubble will start coming out. Operating condition approaching fuel vapor pressure. In that condition, the operating pressure will operate and will reach to the fuel vapor pressure. Here I am showing one pump. Here this fuel outlet, and this it is a motor and it is rotating. Fuel is entering from here and it is going here in this way, and the pressure is increased. Here this you can see here fuel inlet from both the sides. It is this one is this. Here it is entering and this will go here, and this way both sides fuel pump discharge. Here is a check valve, pressure switch and tapping. It is a cartridge canister schematic. Okay, so here is the electrical connector to rotate this shaft here. Here is a motor. Here is a cartridge. This inlet slide valve. These different valves are here. They will maintain the required pressure. These all things are done. Here we have the poke open vent valve, and here is the discharge valve. Here I want to show some plots about the genetic centrifugal pump characteristics. You see here mass flow increase. If you increase the altitude, the height, at the lower height mass flow is more. As you go higher and higher, the mass flow rate fuel is reduced. That we have to take very much. Any centrifugal pump which we have used just now, this is the centrifugal here. The problem in this that as you go in higher altitude, the mass flow is reduced. Feed system block diagram, how this from tank to the engine, how the fuel is entering. Here we have the Mach number, operating altitude sensor. Here is a vent pressure recovery system. Here is the ullage pressure, PU. Then here we have the feed pump characteristics. It is a centrifugal pump here. From here, this is the delta P. It will go to the feed line losses, and then it will go to the engine. And if anything is there, engine flow demand, as per that, as per the demand, this will vary the amount of the fuel. So this is shown a very simple diagram here to understand that what can be happen. Now I will talk about the next. It is called the ejector pump. It is like a Venturi type of the pump. Ejector pumps are smaller aircraft. We use these pumps. In this there is no moving part, only some pipes as shown in this diagram. Only no moving parts. High pressure motive flow source from the engine. Separate motor is required for this. Driven pump for the starting. Dedicated pump on the engine gearbox. Outlet on fuel metering. low efficiency. This is only 30% efficiency. So we are not using in most of the advanced aircraft the ejector as a boost pump. This you can see here, the high pressure motive flow is coming from here, and from here it is inlet and it is motive flow plus induced flow. So in this way the fuel is entering and it is getting some here extra pressure. So this is the principle for the ejector pump. Ejector feed schematic I have shown here. Ejector feed. So here we can see that here is the engine and here we have the motive pump. It is rotating. Here is the backing pump. Here we have the high pressure stage. This is a gear pump. Then we have the bypass flow pump inlet here. It is bypassed from here. Metered flow combustor. Fuel metering unit from here. This goes to the engine. And here high pressure motive supply. It is given from here. And this goes to this pump, fuel injector pump, aircraft feed tank. So in this way, this is the schematic and the principal operation procedure for the ejector feed schematic diagram. Now feed tank scavenging. What is the meaning of scavenging? And scavenging, why we have to do the scavenging? Scavenge pumps to suck up fuel from the remote corner. You know that in the corner some fuel is left and there are very big tanks and there are huge amount of fuel may be trapped. That fuel has to be removed and this process is called the scavenging, and this is done by the help of the scavenge pumps. Scavenging ejectors are also there. Water contamination can be significant. Time between flight insufficient for water to settle down. Water may not be able to settle down due to the vibrations and shaking of the fuel tanks. That time we have to use the feed tank scavenging system. Scavenge pumps are used that breaks down water into the small droplets and then we pump to the engine. Water droplets become frozen, fuel filter blockage. So if this water particles are present in the system and it is expanding, the temperature will further go down and this temperature will make that the water particles will freeze and they may block the fuel filters as well as the nozzle holes or the injector valves which are located for the burning of the fuel. So this scavenging is very much essential to take out the corner fuel and remove the water content from that system. Negative G consideration, we have to see that fuel will migrate towards the upper surface. If the negative G, your aircraft is falling down, the fuel will migrate towards the upper surface. Pump capable of separating out air to inlet. Collector cell kept full and slight pressurized. Feed system diagram, we can see here that how the feed systems, twin engine feed system, physical overview, twin engine feed system, detailed schematic. Here we have the two diagrams. So engine feed system, this is the engine here, left engine is shown here, this is the engine. So from the tank, how the fuel will go to the engine. So here we can see that here the low pressure pump is there, it is pressurizing or the booster pump to other engine from here, and for this it will go here. We have the spar mounted APU pump is here. Here we have the scavenging ejector. Just now I have discussed that this ejector is used to take out the fuel from the corners. Collector cell is also here, which indicates the how much fuel is there. Suction feed is also there. Then we have the motor driven booster pumps. These are the booster pump. Then we have the engine driven LP shut off valve, and then we have here the engine pumps here. So it is a schematic feed of twin engine feed system of any aircraft. Twin engine feed system detailed schematic. It is just a simple one, but here if you see, we have the detailed one. So here APU feed system, This goes to here, starting from the engine feed. Then we have the thermal relief valve. Here we have the cartridge in canister, booster pumps. We have the suction inlet. Here we have the scavenge ejector. Here we have the motive power to scavenge ejector, which we are getting from the engine. And in this way, we are making the system, feed system of the aircraft. Feed system design, if you talk, it is a very critical system to design. Hot fuel operations. Sometimes we need the hot fuel, especially in the cold weather. We have to heat the fuel. Fuel types, fuel vapor pressurized. Design requirement, keep fuel velocity below 10 feet per second. The fuel velocity should not be very high, otherwise it will create the problem for the pumps and all. Feed line should be very much smooth. Thermal relief valve should be fitted, which is sensing the pressure and the temperature, and they are closing and the opening of the fuel valve. Air release valves to separate air from the fuel in case of any failure. Now, fuel transfer. So how the fuel can be transferred? So, fuel consumed from various tanks with predetermined schedule, fuel burn sequence, CG, wing load, tank quantities. As per the CG, if the CG is not balanced, that time we have to transfer the fuel from one tank to another, left to right, right to left. Also from tip tank to the root tank, root to the tip tank, inboard and outboard tank, outboard to inboard tank. Like this we have to shift. This is for the CG location. Wing loading, if we feel that the wings are overloaded due to the high amount of fuel inside that time also we have to transfer from wing to the belly or vice versa. Tank quantities we have to see. Control of the fuel, it can be done by the crew or it can be done by the automatic management by the computer system nowadays. Fuel burn scheduling, twin engine with 2 tanks, cross feed in event of an engine failure plus lateral balance. So we have to see that your aircraft is balanced in all the respect. System design requirement. These are the requirements which I have mentioned here. Mainly there are 3 types of requirement: motor operated valve, solenoid operated valve, and accommodation of failure. In accommodation of failure, we have the fuel will not be trapped, redundancy of the function will be maintained, breakup gravity transfer has to be performed, valve fail to preferred position. These are the design requirement for the system. Fuel jettisoning, it is the last topic. In case of some weight problem or the maximum takeoff weight or the maximum landing weight, if these things are increased, that time, or the weather is not good, that time we have to jettison or remove the fuel within no time inside the aircraft. So, maximum takeoff weight is the one criteria. If it is exceeding, maximum landing weight, if it is exceeding, we have to jettison. Emergency situation after takeoff, if we feel that there is a very bad weather and your aircraft is experiencing some turbulence where your aircraft is not able to sustain, or some engine failures or something is happening, that time also we have to jettison the fuel soon as possible, landing 30 to 45 minutes. So here jettison system example, allow jettison to proceed while engine feed supported, crew workload kept to a minimum to focus to the initial emergency. You know that if the weight is high, then the pilot has to think about how to control that thing. But if you remove this fuel from the fuel tank in case of emergency, then pilot will not much focus on the weight, because weight is sufficiently less and pilot can take the necessary measures to make the aircraft safe landing and the takeoff. Here we have some isolation valves, and these are the pumps. These pumps are fitted to jettison the aircraft. fuel from both the sides. And this you can see during the landing of the aircraft. You will see some amount of fuel is jettisoned if your center of gravity is not balanced. Fuel quantity gauging, we should also be able to measure how much quantity of the fuel is there on the tank. Measure the fuel content in all tanks. The purpose of this gauging is to measure how much fuel is there in each and every tank. Information to both the flight deck and the refuel panel. This information should be available at the refueling. There is a panel I have shown you before, and also in the pilot cockpit it should be available at the flight deck. Mass quantity, how much quantity is stored and how much flow is there. Variation in the fuel properties, how much density, other fuel mechanical and the thermal properties has to be ensured. Stratification, warm fuel on a cold residual fuel. So we should supply the hot fuel in the cold weather condition. Variation in fuel surface due to maneuver. If you are maneuvering, the fuel will be transferring here and there. Tank distortion. In this also, if the tank is also distorted, that time also we should see the gauging. Unusable, ungaugeable fuel, if it is there, we should find out. Integrity regions, volumetric information independent of the primary system. High level sensing, overfilling. Capacitor sensors are used to sense how much fuel is there. Previously we used to have the resistance type of fuel, but now we use the capacitance type of fuel. This measures the air above the fuel, how much air is there. Probe compensator for the variation in fuel primitive. Densitometer, volume information into mass. Temperature sensor. Fuel properties measurement unit. Number and mounted location of the probes. Breakup system. Dissimilar technology to offset common mode failure. Fuel on board reconciled by fuel consumed by the engine. Sensing system, intrinsically safe. Discharge of electrical energy. Fuel load planning, we have to load the fuel in such a way that your center of gravity, your other things are very much safe. Critical on the long range, if you are flying, your fuel should be full. Weather and wind forecasting also is important parameters for the loading of the fuel. 5% of the margin for the inaccuracy. Additional fuel to allow diversion to alternate airfield. Additional fuel to allow 30 minutes flying after reaching the alternate airfield. You should fuel in such a way that if you reach there in your destination, 30 minutes further it can fly. That much amount of fuel every aircraft has to carry. Leak detection. We have to detect the leak, otherwise you will land in a trouble. Accuracy of total fuel on board. Fuel flow meter on each engine. Flow meter inaccuracy, gauging the accuracy. So by this way we can see that whether the leak is there on the system or not. This you can see here. Hours since the takeoff, fuel consumed from the flow meter. Fuel quantity, normal fuel on board on the gauging system. So in this gauge it should fall like this if it is going like this. So leak detection has to be performed. Flow meter inaccuracy errors. So fuel management we have to do. Interface with overall aircraft. Automatic to minimize the crew workload. The fuel management system and its interface, it is shown here. Fuel management systems, FMS, flight management system, overall flight plan. FWC, flight warning computers are used. DMC, displays management computer. Multifunction displays are also used. Overhead fuel panels are used. Fuel quantity information switches to the select pump valve in the event of failure. INS, inertial navigation systems are used. Engine 1, engine 2, engine master switches. Weight of the wheel, advise aircraft on the ground. Power management, loss of electrical power, auxiliary backup, DC. Refuel accuracy, refueling accuracy can vary significantly. Valve closure rate, fuel overshoot, latency in gauging information, error between the nominal and the achieving upload, predetermined limit, auto fuel abort, manual refuel, management software, set off anticipation. Active longitudinal CG control. How to control the CG? It is very, very important. So to minimize trim drag, CG control significant in terms of both acquisition and operating cost. Trim tank longitudinal stabilizer. Without CG control and the CG control. So if the CG is controlled, it should be in this line. But if it is not, you see, lot of variation can be there. Aft, forward. Okay, so this is aircraft CG control example. This is shown in this way. Ancillary systems, we have the thermal sink. We have the additional system in the fuel system that is called the thermal sink, hydraulic systems, unsafe oil fuel temperature, engine oil lubrication, spill fuel temperature can become high fuel, maybe recirculated into the tank, problem with the gauging, maintain tank fuel temperature above the freeze point. And here it is shown the fuel to engine oil cooling schematic diagram. So in next lecture, I will go with the revision, introduction, types of fuel system components, fuel tanks, fuel grades, fuel safety and the precautions. These I am going to discuss. These are the references, Moyer and the Seabridge aircraft systems, mechanical, electrical and avionics systems. Next book is from the same author, Moyer and the Seabridge, design and development of aircraft systems and introduction. Any questions you are welcome to ask. This is my email. In this you can send any queries. I will be very happy to reply. Thank you very much for joining this class and please be tuned for my next lecture that is also depend on the types of aircraft fuel system. These are the topics which I am going to cover, that is the types of fuel systems, fuel tanks, fuel grades and so on. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.